All right, so let's go back to this question here. Again, we're going to apply the implicit differentiation to do that. So that is d e to the power 7x dx equals d cosine of 2x plus 4y, right? And then dx here. Okay, so so on the left-hand side, we're going to apply chain rule. So that is e to the power of 7x, right? Times the derivative of d7x dx, that gives us is a 7. And then on the right-hand side, the derivative of cosine 2x plus 4y, you're going to apply the same logic about this to attack this one. That means you're going to have its negative sine of 2x plus 4y, right, times the derivative of the inside function with respect to x, that is 2x plus 4y over dx. Okay, so exactly chain rule stuff. And then you're going to have its negative sine of 2x plus 4y. And then the derivative of this, so d2x dx is going to give you its 2, and then plus 4 dy dx. Okay, 4 dy dx. And then left-hand side, nothing changed, so it's just the 7 e to the power 7x. Okay, so now you can see that we gonna figure out what is dy dx. Then the problem becomes purely an algebraic operation. So that is, so if we distribute this, that's going to give us is negative 2 sine of 2x plus 4y, right? And then minus 4 sine of 2x plus 4y times dy dx. And then we have 7 e to the power 7x, okay. And then, so you can put everything without the dy dx to the left-hand side. That is 7 e to the power 7x plus 2 sine 2x plus 4y. And then equals this negative 4 sine of 2x plus 4y dy dx. Then you can divide this on both sides, right? So that will give us, well, let's start with the new paper. That will give us is dy dx, equals 7 e to the power 7x plus 2 sine of 2x plus 4y, and then over negative 4 sine of 2x plus 4y. Okay, so we're done for this problem. Okay, so you can see that's the beginning. Takes the derivative with respect to x on both. Chain rule. Simplify, reorganize, calculate, done. Okay, that's how we do the second problem. Okay, the idea it's pretty similar. Okay. So everybody okay with this one? Will there be a question about it is different? No, just the first derivative. Sean, you have a question?
Yeah, I'm still kind of confused on the whole how the sign ended up, the negative 4 sign ended up on the other side.
Negative 4 sine ended up on the other side?
Yeah, so you have negative 2 sine 2x plus 4y minus 4 sine 2x plus 4y. Are you
talking about this step?
Correct, yes.
Oh, so you have question from here to here or from here to here? Which one? This is
Second one.
Second from here to here?
Correct.
Okay. Oh, I just distributed. So negative sign of this multiplied by 2 give us is negative 2 times sine of 2x 4y. And then you have a 4 here. You also have a negative here. So just to give you is a negative 4 sine of 2x plus 4y and then dy dx. It's just a distribution.
I didn't even know you're supposed to do that. So you just multiply basically
Of course.
the sine 2x plus 4y, multiply by 2, multiply by 4, and that's it.
Of course, yes. Because what we want to do is we want to figure out what is dy dx is. So we need to find the corresponding term with dy dx. So that's why we distributed, because this 2 multiply this guy, there is no dy dx get involved. So so we need to isolate the term with dy dx. So that's why you need to do the distribution. Okay.
Thank you.
Sure. Okay. All right. So any other questions, guys? Okay. So if everybody is okay with this, we can move on to the next one. Let's see. Why don't we have the third example in this way? Let's see, y equals x squared plus 1 to the power of 7, x plus 1 to the power of, 24, and then times x cubed, okay, x cubed. And then the problem asks us to use the logarithmic differentiation to figure it out. Okay, again, apply the logarithmic differentiation to figure it out. So, this problem, you can apply the chain rule and then product rule to start. Okay, right? So definitely we can do that. But anytime you see like a multiplication of polynomials, and especially with pretty high order, then the best approach to find the corresponding derivative is to apply the logarithmic differentiation. Why? Because one of the most important property for logarithmic is it can split a multiplication into a summation format, because log of AB equals log A plus log B. Okay, actually it's kind of like a reduce the complexity of the problem. Okay, so let's see how do we work on this problem. So if we apply a natural logarithm ln on both sides, so left hand side is ln of y equals ln of x squared plus 1 to the power 7 times x plus 1 24th, and then x cubed. Okay, and then again, based on the property of the logarithmic, I can first rewrite into this way. Okay, and then the other property about logarithmic is log of a to the power of b. You can bring that power outside of that. That is b times log of a. Okay. So in other words, on the right hand side, you can even simplify into 7 ln of x squared plus 1 plus 24 ln of x plus 1 and then plus 3 ln of x. Okay. And then left hand side is still is ln of y. Okay. And then now look at what we have the right hand side compared to the original one. You know, the derivative for each piece is pretty straightforward. So now we take the derivative with respect to x on both sides. So d ln y dx equals, the derivative of this is 7, right, times 1 over x squared. And don't forget, you need to times the derivative of x squared plus 1. Okay. Plus 24 times 1 over x plus 1 times the derivative of x plus 1. Okay. And then plus 3 times 1 over x. Okay. So that's the derivative for both sides. And if you simplify it, this is going to give you 2x. Okay. And 2x times 7, it's a 14x. So it's a 14x over x squared plus 1. And then plus, the derivative of x equals 1. So it's 24 over x plus 1. And then plus 3 over x. Okay, so that's, again, the right-hand side. The left-hand side, the derivative of ln y with respect to x. Again, you're going to use the chain rule because y is a function of x. So that's going to give us 1 over y times dy dx. Look at the expression on the left-hand side is we want this dy dx. That's what we are looking for. And then, you know, times 1 over y, right? So dy dx actually equals this. Multiplied by y. But my y equals what? Equals this. So replace that. Times and then up down. Okay, so that is the answer. Okay, that is the answer. So you see, doing this way, guys, even if you didn't simplify to the derivative, of course you can distribute and then starting to simplify. But the approach, it is simple and clean. Okay. It's way better than, you know, apply the product because you have to group one of them and then apply the product rule and then chain rule and then another one of product rule. Okay, so the logarithmic differentiation makes things easier for this particular problem. Okay, so let's take a moment to see if you have questions or not.
Where did you get 14x from? Did you multiply by the derivative of x squared plus 1?
Yes. So this part, wonderful, great question. So this, the derivative of x squared plus 1 equals 2x, right? So this part actually is 2x. So what I did is I used 2x multiplied by 7. That gives us 14x here. Great question. Mm-hmm. Any other questions, guys? All good with this?
Yes.
Okay. Okay. Now let's see. What kind of questions I have? Wow. Okay. So let's continue to practice another similar one. So let's see. Equals. Okay. Let's look at this one. Y equals x times sine x over square root of x plus 7. Still, use the implicit, use the logarithmic differentiation to figure it out, okay, for this problem. And the logic for example 4 is identical to example 3. So the problem asks you to use logarithmic differentiation, okay, to do that. So if you apply the logarithm on this side, natural logarithm, this is what you get. And then apply the properties of logarithmic, you're going to have this ln of x times sine x, right? And then minus ln of square root of x plus 7. Let me write it into this way. And even more, the right hand side can be written as ln of x plus ln of sine x, right? And then minus 1 over 2 ln of x plus 7, okay? And then of course our left hand side always is ln of y, okay? So now we take the derivative with respect to x on both sides. And then our left hand side is 1 over y times dy dx. Our right hand side, this is going to be 1 over x, right? And then ln of sine x equals 1 over sine x times the derivative of sine x, right? And then minus half. The derivative of ln x plus 7 equals 1 over x plus 7 times the derivative of x plus 7. Okay. And then we use another paper to do that. So we're going to have it 1 over y times dy dx equals 1 over x. The derivative of sine x equals cosine x, right? So you have cosine x over sine x. Actually, it's cotan x. Okay, and then minus 1 over 2 times 1 over x plus 7. The derivative of this part equals 1, so you have minus 1 over 2 times x plus 7. Okay, and then so that's the simplification for the right hand side. And then on my left is always 1 over y dy dx. So dy dx is going to be, let me still use bracket, times y. And where is my y? Go back to here. So replace that. And then times x okay, so that gives you the answer for this problem. Okay, that's the answer. Okay. So take a moment to see if everything is okay. Okay, so if everybody is following this problem, and then let's move on to the other one. Oh, by the way, guys, you're gonna need the derivative of these trig functions, like the derivative of sine equals cosine, derivative of cosine equals negative sine, derivative of tan equals secant squared, derivative of cotan equals negative cosecant squared, you know, those kind of things. Okay, so you remember we have 6, so make sure you do that review before you start the test, because you're gonna need them. Okay, there are gonna be some problem that associated with the derivative of those trig functions. Okay. Let's see. Maybe let's have another problem like this. So given the function, let's see, x squared plus 3x plus 9. Okay, plus 9. And then let us have an interval, let's see, from maybe from -1 to 7. Okay. So remember the mean value theorem we discussed from 4.2. That is, if a function is continuous, right, on a closed interval and is differentiable in the corresponding open interval, then they're going to exist at least a number c such that f prime of that c equals, right? So that's what we call the mean value theorem, the MVT. Okay. So this question, it asks you, okay, if the function is given here, okay, and the interval is given to here, -7 to -1 to 7, and then figure out the corresponding value of c, such that the derivative evaluated at c equals fb minus fa over b minus a. Okay. So actually, this type of question is pretty straightforward. So what we'll do is we just calculate fb and fa. So f7 is 7 squared plus 3 times 7 plus 9. That is 49 plus 21, and then plus 9, right? So that gives you, it's 79. Okay, 79. And then f of -1, which is -1 squared plus 3 times -1 plus 9. So that gives you, it's 1 minus 3 plus 9. That gives you, it's 7. Okay. So we got f -1, f7. So f7 minus f -1 over 7 minus -1. It gives us is 79 minus 7 over 8. Okay. So it's 72 over 8. Okay, over 8. And then turns out this equals 9. Okay, this equals 9. And then we're looking for the derivative at the value c equals 9. The function is given, so the derivative is 2x. Oops. So the function here equals x squared plus 3x plus 9. Okay, so the derivative equals 2x plus 3. So you're looking for such a number c such that the derivative equals 9. So you can solve that. That 2x plus 3 equals 9. So 2x equals 6. X equals 3. Okay, and then this is the corresponding value c such that the derivative equals this. Okay, so that's a simple application with the mean value theorem. Okay.
Will that formula be given in the question to kind of alert us that we need to use the mean?
Yes, I believe so. Yes. This one will be given, yes. Okay, so any other questions? So is the pace okay so far? Too fast, too slow, or okay? Okay. Okay. Just want to make sure. All right. So the other type of a question that a little bit fast. Yeah. So the good thing is we recorded because I do want to make sure that I cover as much as I can, so to serve you guys for test two. Okay, so if it's a little bit fast, I'll try to slow down a little bit. Okay, so the next question, like a general type of question you will see in test two, is give you a function, ask you to find the critical point, and then ask you to find the corresponding increasing or decreasing interval. Okay, so that's like a very typical question you will see during the test, especially the second half of the test. Okay, so I don't know, so why don't we, let me see some problems. Trying to see if there is a proper example I can discuss. Okay, so why don't we do this? Fx equals, let's see, x cubed minus 8x squared. Okay, so the question is, so find the critical point and also find the increasing, decreasing open intervals. Okay, so those two also, and also the local extreme values. Okay, local extreme values. So this is going to be a very typical question you will see in test 2. So to find the critical points, we take the derivative, right? That's going to give us this 3x squared minus 16x, right? 16x. And then you set the derivative equals 0. That is 3x squared minus 16x equals 0. Oops. So for here, you have to be careful. If you factor 3x out, and then you're going to have x left, but on the second part, you're going to have 16 over 3. Okay, because you are factoring 3x out. So that gives you that x equals 0 and 16 over 3. Okay, 16 over 3. So apparently, guys, the derivative function 3x squared minus 16x, you don't have any values that can make your derivative undefined or does not exist, right? So we only focus on, okay, which values can make my derivative equal 0. So that's why we solve for that. We got our two critical points. But sometimes, when you take the derivative, especially the derivative expression is in a rational format, okay, and then the denominator might involve with term of x. So at that situation, you have to be very careful, because the values that can make the denominator equal 0 is also the critical point. Okay, because definition of the critical point is those values either make the derivative equal 0 or the derivative at those values does not exist. I believe the video I posted earlier, it shows exactly same trick, right? That because the derivative you do have a fraction form, and the denominator does have some values, can make the derivative does not exist. Okay, so make sure about that. So go back to our problems here. So those are the two critical points, and then I'm starting to looking for the increasing, decreasing interval and the corresponding local extreme value. So let's use a new paper, and then continue. So put this into a line, label 0, label 16/3. Remember, my function here is a polynomial, and the domain of a polynomial is overall numbers. Okay, so those two critical points partition my interval into three parts. That is, from negative infinity to 0, and then from 0 to 16/3, and then 16/3 to positive infinity. Okay, so what I like to do, again, remember, let's do this table, and then, right, so let's do x, let's do sine of the derivative. Okay, so in other words, you pick a random number from this. Let's say I take x equals -1. In this case, I take maybe x equals 2. In this case, I don't know, x equals maybe 6. Okay, it's just a random pick it. So the derivative function is 3x squared minus 16x. Okay, or you can do it. Remember, so it's 3x times x minus 16/3. Okay, in this way. So let's try to verify this. When x equals -1, 3 times a negative number, it's a negative number. Okay, -1 minus 16/3, so still a negative. So you see, you have negative number multiply another negative number. So it turns out the sign of its derivative at -1, it is positive. Okay, it is positive. So, okay. So of course, guys, you can definitely plug in -1 there. So 3 times -1, and then -1 minus 16/3. This. So you can see, turns out it's a 3 times, it's going to give you its 19/3. Turns out it's going to give you its 19. Okay, it's 19. But the important thing is we really don't care about the exact value. We care the most is the sign of its derivative evaluated at this. So same logic. The derivative evaluated at 2. So guys, you can plug in. So 3 times 2 minus 16/3. Apparently, guys, this is positive. This number is between 5 and 6. It's 2 minus this number. This is negative. So you have positive times negative. So overall, this is going to be negative. Okay, so the sign here is negative. And of course, the derivative evaluated at 6. Last value we picked. So it's a 3 times 6, and 6 minus 16/3. So you see that this part is positive. This part, 16/3, it is number between 5 and 6. So overall, this is also positive. So multiplication of 2 positive. This also give you a positive sign. So the sign here is positive. So go back to here. This table can tell us everything. Why? Because the increasing interval, so let me label that. So the increasing open interval going to be negative infinity to 0. Oops. Union 16 over 3 to infinity. Okay. While the decreasing open interval will be from 0 to 16 over 3. Okay. And also, you see you have increasing and then decreasing based on the right, increasing, decreasing, and then increasing based on the first derivative test at x equals 0. You have a what? Local maximum, right? Because you're going up and going down. So it's a local max. And then you're going down and going up. So at x equals 16 over 3, you have a local minimum. Okay, local minimum. So that complete this examples here. Okay. So we actually did a few of them, right? So
will there be anything on the second derivative rule?
No. No. The I don't think so. Let me see. Yeah, I think since we didn't cover too much related to the concavity, so but there's some like a graph problem. Okay, so give you a graph and then ask you to identify where is concave up, where is concave down. So there is really no like a calculation based on problem for the second derivative and its concavity. Okay, it's a good point. Okay.
So we'll have to know the second derivative for that to find concave up, concave down, correct?
Like I said, there's some graph problem. For example, you draw a graph and ask you to identify, from which interval is concave up, which interval is concave down, something like that. Yeah.
Oh, I got you. So you're just looking at a graph and interpreting it. Cool.
How did you find the local max and local min? Camera asked. So this goes back to what we call the first derivative test. So you can think about this. So around the two sides of a critical point. So if the left-hand side your function is increasing, and then while passing from that critical point, your function is decreasing. So in this place, you have increasing on the left, and then decreasing on the right. That means if it's increasing, so the derivative is greater than 0, and if it's decreasing, the derivative is less than 0. If that's the case, so at this point, you're going to have a relative or local, right? Same name, maximum. Okay, maximum. While for the other case, so if you have decreasing on one side at first and then increasing, so you will see that you're going to have a relative mean, right? So if it's decreasing first on the left hand side, it's less than 0. On the right hand side, it's greater than 0. So actually it's based on, this is what we call the first derivative test. So based on this test, associated with our table conclusion, and then get what we want, because going up, going down, local maximum, going down, going up, local minimum. And then if you want to figure out, okay, what is the local maximum value? So in this example, remember at x equals 0, it has a local max. So you have to plug this 0 actually back to the original function, which is here. So f of 0, which is just plugging 0, 0. So f of 0 is 0. Okay. And then if you want to figure out what is the local minimum, so you need to plug x equals 16 over 3 to the original function to find that specific value. Okay, so I think that's gonna helps. Okay. So, good question. Any other questions, guys? Okay, so if this part is good, let me do one last question. Okay, and then I'll let you to prepare and then start your test too. So the last question, actually, I just want to repeat a little bit from the problem I already uploaded. Okay. Online, but I'm not sure like how many of you watched the video. Okay, so let's let me go through quickly. Give me 1 second. So the problem that, let me see if I can find it. Okay, so yeah, why don't we just go through this part again? So this is the function. Okay, g of x equals x times square root of 2 minus x squared, and then it asks me two questions: find the open intervals for increasing, decreasing, and then find those local and absolute extreme values here. So different with the previous examples, which most of the time the function we work are polynomials. So this function is not a polynomial, okay, but instead it gets involved with a radical, a square root. So the problem didn't give us any specific interval. Then you have to find the corresponding domain of this given function first. So how to figure that out? Well, the key is the square root. Make sure that in a real number system, the inside of the square root must be greater or equal than 0 all the time. Okay, so that's how to get the domain. That is 2 minus x squared must be greater or equal than 0. Okay, and then this inequality equals x squared is less or equal than 2. So if you solve for this inequality, that's gonna give you is my x is between negative square root of 2 to square root of 2. So that's my domain. If I write in an closed interval notation. Okay. So this really, guys, it is the key to start. Okay, so this is the playground, right? So you'll play this problem. Okay, so make sure that you got this part correct. And then after that, you know, I rewrite my function into an exponent format, and then I take the derivative. Of course, you're gonna apply the product rule at first, and then associated with the chain rule, right? This part you're going to use the chain rule. So after the simplification, this is what you got here. Okay, and then I think one of the other looks like a tricky part is, you know, if you write this, go back to the format with square root. This is what you have. Okay, and then in fact you can combine this into one rational. That means that this one have the same denominator as this. So as you can see that you multiply square root of 2 minus x squared over itself, that gives us this. Well, but magically on the top you have square root, so it cancel out, only have 2 minus x squared. And then so that's why we can combine this as one. So this is like the simplified expression for my derivative. As I mentioned, the expression is rational, and then you need to calculate the values of x which can make the denominator equal 0. That is 2 minus x squared equals 0. You got square root of 2 and negative square root of 2. Those two are also critical points or critical values. Okay, critical values. And of course, because at those two values, the derivative does not exist. Okay. Meanwhile, when you set a numerator equals 0, you got x equals 1 or negative 1. Those two values, they're going to make my derivative function equal 0. Okay, so you see in this example, it does include both types of the critical points we learned. Either make my derivative equal 0 or make my derivative not exist. Okay, so you have actually 4 critical points in this example. And then you label that. Remember, those are our playground, the domain. And then, so very interestingly is, the left endpoint and right endpoint, they are also my critical points. So, and then of course negative 1 and 1 here. So those actually 4, it partitions my interval into 3 parts. Negative square root of 2 to negative 1, negative 1 to 1, 1 to square root of 2. And then you're starting to pick random numbers from each, and then to do the evaluations here. Okay, evaluations. And of course you can see the like the explanation, because I already recorded a video and then posted it online here. Okay, but I just want to let you know that the key to solve those types of questions, the starter is pretty important, is to find the current domain first, especially you have a square root. Okay, so yeah, I think right now it's 12:10, so I'll stop here. And okay, so good luck, guys, and okay. Oh, and don't forget, I think the due for the 2 extra bonus is also today, right? So after the test, and then if you haven't submitted, go ahead to submit that. Okay. So if you have questions, stay here, and I'm here. If not, guys, good luck. Thanks.
Is there going to be a problem like this where we're going to have to find the domain?
If the problem like this give to you, you're going to automatically need to find the domain. Yes, first.
Okay. What can I see the difference between that type of problem and a problem that actually gives you the domain, so I can kind of look out for the differences in it, so I know when I have to solve to find the domain?
Well, normally if the function is a polynomial, for example, if fx is like x times 2 minus x squared, so you know the polynomial, then the domain is always all real numbers. Okay, so it includes everything. But if the function get involved with radicals, okay, or some, I don't know, like h of x, something like this, like x over, I don't know, x squared minus 1, like a rational expression, then you need to figure out the domain, because the domain for this function here is all real numbers except negative 1 and positive 1, right? Because if you set the denominator equals 0, that are going to give you x equals 1 or negative 1. And those two numbers are going to make the denominator equal 0. We know that, yeah, so we need to get rid of from all real numbers. So,
thank you.
Sure. Any other questions?
One more. How will the bonuses be added to the test? Because they're plus like a certain point.
I already mentioned it's just added to your test grade. So for example, if you test 2, you got 95, and then if you submitted the third bonus points, it's 5 points extra. So your test is 2 grade is going to be 100. That means 95 plus 5.
Wonderful. Thank you very much.
Sure. Any other questions, guys?
Oh, can I ask a question?
Yes. Thank you.
Are inverse trigonometric function and relative rates are included on the exam?
Related rates, no. But the trig inverse, no. But a regular trig derivative, yes. For example, what is the derivative of tan? What is the derivative of cotan? This,
Yes.
for sure, you need to know that. But yes, so those relative rates and inverse, no. Okay?
Oh, okay. Thank you very much.
Sure.
Okay. Thank you, Bob.
Bye.